memiliki pola pikir yang lengkap. Kemarin terakhir ketika puasa kemarin ya, menjelang libur Lebaran, sudah membahas persoalan atau contoh 7.5. Kita harus bergerak menuju ke selanjutnya, pembahasan selanjutnya, yaitu magnetic flux density dengan kaitannya pada persamaan Maxwell. Nah, ya persamaan Maxwell ya. Sudah aku pilihkan, jadi YouTube itu sudah kulihat ya, jadi aku sudah bisa membayangkan kalau kamu dummy, gak punya memori yang zaman dulu-dulu atau belum pernah melihat, maka YouTube tersebut mewakili kemampuan kita untuk membayangkan, karena elektromagnetik itu nggak sama seperti matematika saja ya. Jadi sudah dicontohkan yang kemarin, plus minus itu berdasarkan cerita atau info atau arah, karena itu kita bermain pada konsep vektor gitu ya. Nah, ini aku ngecek kok Dwike-nya nggak ada, entah Dwike itu masih di kampung atau not connected dengan jaringan. Aku menawarkan kepada yang hadir ini 13 orang ya member kuliahku, siapakah yang berkenan untuk donasi atau share screen untuk materi-materi yang sudah aku lempar di grup ya. Aku lempar di grup itu ada sekian materi, mungkin 4 tadi itu, dan itu bisa membuat kita lebih mendalami dan memiliki bayangan tentang apakah magnetic flux density atau kerapatan flux magnet ya. Flux itu berarti garis-garis gaya magnet ya, dengan magnetic density ada satu yang membahas perbedaannya, kemudian yang lainnya membahas karakteristiknya, jadi modelnya bagaimana. Silahkan aku tawarkan kepada yang berada di sini, adakah yang berkenan untuk share screen? Mengapa selalu aku tawarkan? Supaya aku punya teman. Kalau aku nge-share sendiri, kemudian ngomong sendiri, aku nggak tahu apakah ada engagement di kejauhan sana ya. Karena kebutuhan itu engagement, tautan, sehingga aku tidak mubazir ya ngomong seperti ini. Tapi kalau tidak ada ya, aku tunggu saja. Kamu sudah bisa melihat apa-apa yang aku share melalui WhatsApp. Monggo silahkan. Oke, yang bisa saja ya. Kalau nggak bisa, silakan buka WhatsApp yang kirimanku di WhatsApp ya. Itu kan aku selalu letakkan di situ agar apabila ada yang lagi berhalangan atau memiliki kendala di lapangan, ada yang bisa dilihat berikutnya. Nah, menuku kali ini memang hanya ini, karena aku tidak bisa mempercepat seperti apa yang kuinginkan, ya karena juga terkait seperti pengalamannya Mas Ruri yang di kejauhan, hujan deras, sinyal agak ngelek, jadi tidak bisa berinteraksi dengan baik. Itulah mengapa aku selalu men-share apapun di WhatsApp group agar tidak ada yang ketinggalan ya. Mungkin yang tidak bisa aku share itu kalau menerangkan contoh soal, karena harus hadir di laman atau harus hadir di etol. Tapi kalau secara teoritis untuk kemudian bisa kau pelajari dari sana, bisa saja ini kamu jadikan referensi semua ya. Insya Allah dengan melihat sekian kali ini 1, 2, 3, 4, 5 kirimanku, setidaknya kalau 50% itu harusnya bisa dapat ya, loadingmu itu harusnya bisa dapat. Ya, kalau gitu sambil aku nge-share IG-nya research groupku ya, untuk memberikan inspirasi padamu. Sekarang semuanya itu sudah berbasiskan medsos juga ya.
Lazada 11.9.000. Beli sekarang.
We imagine magnetic flux being a series of lines running from the North Pole to the South. If we take a wire and cut through this magnetic flux, an EMF is induced between the ends of the wire. Here the wire is being passed through the magnetic field between two small ceramic magnets. The magnets are held in position on a U-shaped piece of steel. Notice that the faster the wire is moved, the greater the EMF induced. The voltage produced depends upon the rate at which the magnetic field is being cut. If we move the wire faster, use stronger magnets, or use several turns of wire in the form of a coil, then the voltage is higher. The voltage produced, that is the EMF, is equal to the rate of cutting of the magnetic flux. That is written here as d phi by dt, where phi is the amount of magnetic flux and t is the time in seconds. We can use this definition to define magnetic flux. That is, a flux of 1 Weber per second is being cut if the EMF is 1 volt. Next, flux density. If we imagine a sheet of area 1 square meter perpendicular to the magnetic field, so that the lines of the magnetic flux cut through it, and then we take that sheet and turn it round and look at the flux cutting through. If the total flux cutting through is 1 Weber, then that is a flux density of 1 Weber per square meter. Webers per square meter are also called Tesla. So, a flux density of 1 Tesla is 1 Weber per square meter. Thank you for watching.
Difference between magnetic flux and magnetic flux density. Definition. Magnetic flux is the amount of magnetic field passed through a surface, such as a conducting coil. Magnetic flux density is the amount of flux passing through a defined area. Magnetic flux is denoted by phi b or phi. Magnetic flux density is denoted by B. SI units. SI unit is Weber, WB in magnetic flux. Whereas in magnetic flux density, SI units are WBM minus 2, that is Weber per meter square, Tesla, T. Nature of the quantity. Magnetic flux is a scalar. Magnetic flux density is a vector.
understand about magnetic flux. This is a magnet. This is the magnetic field around it. We know these magnetic field consist of magnetic lines of force, which are passing from north pole to south pole of the magnet. Now take a small cardboard. This is its surface. Place this cardboard inside magnetic field, like this. Observe some magnetic lines passing through surface of cardboard. Let's say 3 magnetic lines are passing. These 3 magnetic lines passing through this surface gives magnetic flux. Observe this line is not passing through surface, so this line is not counted. Similarly, other lines that are not passing are not counted. Magnetic flux is defined as the number of magnetic field lines passing through a surface placed in a magnetic field. Magnetic flux is denoted by symbol phi and is measured in units called Weber. Now rotate cardboard and place like this. Observe, cardboard is still in magnetic field, but number of magnetic lines passing through its surface is 0. As no magnetic lines are passing, magnetic flux is also 0. Now place cardboard surface, like this near pole of magnet. Observe, 6 magnetic lines are passing. Magnetic flux is increased when compared to cardboard placed here. We know at poles, magnetic strength is more. So more magnetic lines pass through surface. Therefore, magnetic flux is more at poles when compared to here. Now place cardboard outside magnetic field. Observe no magnetic line passes through surface. Therefore magnetic flux is 0. We can say magnetic flux depends on magnetic field strength and how surface of the object is placed inside magnetic field. Now let's understand what is magnetic flux density. In magnetic flux we considered whole surface of cardboard. But in magnetic flux density, we consider only unit area of the surface. Unit area equals to unit length into unit width. If we consider CGS system, we take unit area equals to 1 centimeter length into 1 centimeter width. We have unit area equals to 1 centimeter square. Similarly, if we consider SI system, unit area is 1 meter square. Place this cardboard in magnetic field, such that angle between cardboard and magnetic lines is 90 degrees. Observe magnetic lines are passing through cardboard surface. These are called magnetic flux. Again observe some magnetic flux passing through this unit area. This magnetic flux passing through unit area is magnetic flux density. Magnetic flux density is defined as the amount of flux passing through a unit area at right angles to the magnetic field lines. Magnetic flux is denoted by B and is measured in units called Tesla, Weber per meter.
English is my second language.
Masih ada 2 ya.
Hello everyone, this is K.C. Koteshwarama, Assistant Professor of EC Department from Institute of Aeronautical Engineering, Hyderabad. Today I would like to discuss about magnetic flux density, and then we will derive one Maxwell's equation from magnetic flux density. That we will see now. So if you go for magnetic flux density, that is represented with the symbol capital B. If you go for electric field, electric flux density is represented with capital D, but whereas magnetic flux density is represented with capital B. And this is similar to D in case of electric field. If you take D relation in case of electric field is given as D is epsilon naught into E. If the medium is a free space, then electric flux density D will be given as epsilon naught into G, where epsilon naught is permittivity of free space and E is electric field strength. Similarly here, if you go for magnetic flux density B, that is related to permeability of free space, which is given as mu naught, and magnetic field strength as H. And this magnetic flux density is linked with mu naught and H as B will be given as mu naught into H. B is magnetic flux density, that is the product of permeability of free space and magnetic field strength. So here mu naught we can call as permeability of free space. Its value is constant, which is 4 pi into 10 to the power of minus 7, and units for this mu naught are Henry per meter. And if you take magnetic flux lines representation is always from north pole towards left. If you take electric flux lines always starts on the positive charge and the ends on negative charge. Similarly, here magnetic flux line starts on north pole and the ends on south pole. And magnetic flux density and magnetic flux relation is given as magnetic flux psi is equal to integral of B dot ds. If you take magnetic flux density B, that will be given as flux per unit. Here this is B. This B is flux per unit area. And to get flux value, we have to multiply B with ds, and to get the total value, total flux, you have to integrate that. That is given as equation 1. Flux is linked with flux density as flux equal to closed integral B dot ds. That integration is over a surface. And here if you go for the units of flux, magnetic flux is given in Webers. And magnetic flux density is Webers per meter square, or you can call it as Teslas. So the units of magnetic flux density are Webers per meter square or Teslas. And if you take magnetic flux here, magnetic flux lines always starts on north pole and ends on south pole, I told you already, and always it requires a closed surface. But whereas if you go for electric flux lines, they don't require a closed surface. So as electric flux lines are not taking a closed surface, if you take electric flux lines, its relation is closed integral D dot ds equal to Q. But whereas in magnetic flux lines requires a closed path always, and that will be given as closed integral B dot ds equals to 0. And what we can say here is an isolated magnetic charge does not exist. That means if you cut a magnet into smaller pieces also, then it always has both south and north poles. And the total flux through any closed surface in a magnetic flux will be 0. So here, if you observe the relation closed integral B dot ds equal to 0, here magnetostatic field is not conservative, but magnetic flux is conservative. What it means is, if you take magnetostatic field, closed integral H dot dl is not 0. Closed integral H dot dl is always equals to J. So from that, what we can say is magnetostatic field is not conservative. But if you go for electrostatic field, closed integral E dot dl equal to 0. That says the electrostatic field is conservative. But here magnetostatic field is not conservative, but magnetic flux is conservative. As magnetic flux is conservative, closed integral B dot ds equals to 0.
Lazada Tebas 9.000. Beli sekarang. Lazada.
Make any equation no problem with Chegg. Finish your semester.
And now if you take magnetic flux relation, which is closed integral B dot ds over a surface, which is equal to 0, and now I am trying to apply divergence theorem to that equation. What divergence theorem says is, divergence theorem gives the relation between surface integral and volume integral. So now here, if you apply divergence theorem to closed integral B dot ds to this term, then that will be written as del dot B into d. So now from this equation, this entire product must become 0. But dv never becomes 0, then the other term in the product must be 0. Then from that del dot B equal to 0. This del dot B equal to 0 is given as fourth Maxwell's equation. So fourth Maxwell's equation is obtained from magnetic flux density term, which is represented as B. And that fourth Maxwell's equation is del dot B equals to 0. And another point we can see under magnetic flux is magnetostatic field is not conservative, but magnetic flux is conservative. And one more point is magnetic flux lines always starts on north pole and the ends on south pole, and always it requires a closed path. This is about magnetic flux density and Maxwell's equation. So this magnetic flux density gives us the fourth Maxwell's equation. So now here I'm going to conclude this Maxwell's equations for static EM fields. Or I'm going to describe all the four. I'm going to give the summary of Maxwell's equations for static fields. If you observe Maxwell's equations for static fields, we have two Maxwell's equations for electrostatic fields and two more equations for magnetostatic fields. And if you take two Maxwell's equations for electrostatic fields, in that first one is del dot D equals to rho. That is obtained from Gauss law. So del dot D equals to rho V, which is the first Maxwell's equation in differential form. And the same in integral form is closed integral D dot ds equals to closed in here volume integral rho V d. And that is due to Gauss law. And the second Maxwell's equation for electrostatic field is del cross E will be given as 0, which is differential form, or we can call that one as point form, which is equals to closed integral E dot dl equals to 0. Now the integration is over line. And that is obtained due to the fact conservative nature of electrostatic fields. As electrostatic fields are conservative, closed integral E dot dl equals to 0. These are two Maxwell's equations for electrostatic fields. And if we take Maxwell's equations for magnetostatic fields, in that first Maxwell's equation for magnetostatic field are that we can take as third Maxwell's equation is del cross H equals to J, which is obtained from Ampere's law. Del cross H equals to J is the representation of Ampere's law in differential form. And if we can take the same one in integral form, closed integral H dot dl over a line equal to J dot ds over the surface. And the fourth Maxwell's equation are the second Maxwell's equation for magnetostatic field is del dot B will be given as 0. Del dot B equal to 0. That is due to the fact non-existence of magnetic monopoles. That means there is no north or south poles isolatedly. The combination of both north and south poles only existed always, and that the same equation in integral form is given as closed integral B dot ds equals to 0 over a closed surface. This is about Maxwell's equations for static EM fields. 2 for static electric field, 2 for static magnetic field. Then by combining those, we have 4 Maxwell's equations for static EM fields. This is about magnetic flux density and Maxwell's equations. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.
Terakhir,
Hi guys! In this video we're going to be looking at the strength of the magnetic field lines and field strength, magnetic flux density, rate of the magnetic flux, magnetic field lines and field strength, magnetic flux density, and we'll finish with the summary. We're now going to discuss the strength of magnetic field. Imagine that we place two bar magnets at opposite ends of a desk, separated by a relatively large distance. We find that they do not move with respect to each other. They do not seem to repel or attract when the poles are aligned. So we would expect these magnets to attract each other and therefore to move towards one another, but in fact they remain stationary. This is because the magnetic fields of each magnet at this distance are too weak to produce a significant force on the other. So close by this magnet, we have a strong force, which means that the magnets would attract each other if they were close together. However, at this distance, the field is a lot weaker, and therefore the force on this magnet is too small to be attracted to the other magnet. As we bring one of the magnets closer to the other, the magnet experiences an increasing force due to the field of the other magnet. So now that these two magnets are closer together, they experience a larger force towards each other, and therefore they attract. Magnetic field strength increases as we move close to the source of the field. Here we've drawn the magnetic field lines of a bar magnet, and it turns out that as we get closer to the magnet itself, which is the source of the field lines, there is an increase in magnetic field strength. This corresponds to a magnetic pole experiencing a greater force at closer distances to the source. So here we have a big bar magnet in the center, and for this magnet here, which is separated by quite a large distance from the source, we see that the force on this magnet, which we're going to call F1, is fairly small. And notice that the force on the south pole is in the opposite direction to the force on the north pole, because the south pole is repelled by the south pole and the north pole is attracted to it. Now let's consider this magnet, which is much closer to the source. This is going to experience a much greater force, which we're going to call F2. And again, notice that the south pole is repelled by the south pole of the source, whereas the north pole is attracted towards the south pole of the source. And we know that F2 is greater than F1. We're now going to talk about how magnetic field lines can indicate magnetic field strength. We can gauge the strength of magnetic field by looking at how closely the magnetic field lines are spaced. So in the two examples below, we have a current carrying wire, and current is in the upwards direction for both wires. Remember that we can use the right-hand grip rule to show the direction of the field lines. If we point our thumb in the direction of the current and curl our fingers round, this will show us the direction of the field lines. And you can see that the magnetic field lines are curving in an anti-clockwise direction. And in these two examples, one of the magnetic field lines are very dense, whereas these magnetic field lines are much more sparse. Closely spaced lines indicate a stronger magnetic field. And we can see that closer to the wire, we have very dense magnetic field lines, and further away, we have much more sparse magnetic field lines. And this means as we move outwards from the wire, we have a decreasing magnetic field strength. If the lines are equally spaced, this signifies that the magnetic field is uniform. So these magnetic field lines are all equally spaced from one another, and this means that this magnetic field is uniform. With this knowledge, we can see that the magnetic field strength of a bar magnet is strongest at the poles. At the poles are where the field lines are most dense, and so the field is strongest. Further away from the poles, we see that the field lines are much more sparse. This can be demonstrated by placing a paperclip near to a bar magnet. A paperclip is made from steel, and although it is not a magnet, it still experiences a magnetic force, because magnets can attract not only other magnets, but some kinds of metal, like certain types of steel. This paperclip is going to move directly to one of the poles on the magnet, and we see that it is moved from its initial position up onto the pole of the magnet. And this is because the field is strongest at the poles, and therefore these regions result in the greatest attractive force on the paperclip. So here's our paperclip. It's experiencing a force towards the middle, F1, a slightly greater force, F2, but the greatest force of all, F3, is towards the pole. The measure of the strength of a magnetic field is known as the magnetic flux density, and we give the symbol B to this, which is why we sometimes refer to a magnetic field as a B field. Looking at an example of a bar magnet again, we look at the magnetic flux density in 3 different regions. Since we know that the strength of a magnetic field is greatest at the poles, we know that B1 is greater than B2, which must be greater than B3. The commonly used unit for magnetic flux density is the Tesla, or T. And if we measured the magnetic flux density at the pole of a bar magnet, we'd find that it was about 0.01 Tesla. And this is because the magnetic flux density of a bar magnet is very small. We define the magnetic flux density as the density of the field lines in a given region. For example, in these 2 cases here, we have B1 and B2. And the more lines that there are through a certain region, the greater the magnetic flux density. And because B2 has more lines through this area in the black square, this means that the magnetic flux density, B2, is greater than the magnetic flux density, B1.
Hey guys, I hope you enjoyed the video. If you're looking for an amazing A-level physics resource, join me today in my series of engaging bite-sized video tutorials. Just click the snap reply smiley face, and together let's make A-level physics a walk in the park.
Oke, alhamdulillah ada 5 item ya yang saya share padamu. Nah, seperti biasa setelah loading, setelah melihat kita loading ya. Kalau mau aku kasih semacam kayak keyword antara electric field atau magnetic field, medan magnet, sama magnetic flux ya. Magnetic flux. Ada yang kita sebut bahasa Indonesia kerapatan medan magnet sama kerapatan garis-garis gaya magnet. Flux itu garis-garis gaya magnet. Nah, tadi sudah digambarkan, mungkin yang lebih mengena di yang video ketiga yang suaranya Kak Robot itu. Kalau antara magnetic density atau kerapatan medan magnet dengan kerapatan garis-garis gaya magnet, perbedaannya tuh cuman di tempat mengukurnya, gitu ya. Apakah kerapatan magnet itu memiliki pengaruh atau dipengaruhi oleh garis-garis gaya magnet? Jelas. Kalau di video pertama, dari kutub utara ke selatan, ketika menarik itu ya, ketika dia menarik kutub yang berbeda jenis, maka dia mengeluarkan garis-garis gaya yang digunakan untuk merekatkan kedua ujungnya. Nah, garis-garis gaya itu memiliki jumlah yang kemudian di video terakhir disebutkan itulah yang kita sebut sebagai kekuatan medan magnet, field strength-nya. Nah, kalau kita lihat antara garis-garis gaya itu, bila kita total, kemudian kita lihat di permukaan, di depannya jadi di total, kemudian kita ambil semacam permukaan, maka keseluruhan atau sejumlah garis-garis gaya tersebut akan menimbulkan kerapatan magnet tertentu. Nah, kerapatan magnet tertentu itu diterjemahkan oleh video terakhir yang mbaknya paling cantik tadi sebagai kemampuan untuk melakukan daya tarik-menarik ya. Tadi kalau agak jauh kemampuannya rendah, kalau semakin dekat kemampuannya tinggi. Sama juga seperti itu. Nah, mungkin ada yang bertanya, Bu, bagaimana membuat medan magnet itu membesar atau menambahkan flux atau semakin banyak garis gaya magnetnya? Nah, itu terkait dengan adanya arus yang berpindah. Jadi, kemarin sudah diinfokan di episode kamu ketika awal di kelas 1 bahwa ada yang namanya electric field strength, elektrik ya, sifatnya elektrik, kuat sinyal yang elektrik. Sekarang kalau yang diukur itu apanya, elektriknya atau magnetiknya? Yang bisa terukur itu adalah elektriknya. Magnetiknya di mana? Magnetik sama elektrik itu adalah couple atau sesuatu yang kita sebut duet. Ada elektrik, pasti ada magnetik, tapi yang mudah diukur adalah elektriknya. Tadi juga diinfokan kalau kerapatan medan magnet itu ukurannya adalah Weber. Tetapi kalau kerapatan flux magnetik ukurannya itu adalah Tesla. Kenapa? Karena kita mengukurnya adalah Weber per meter persegi. Jadi ada luasannya. Kenapa kok dikasih luasan? Karena kita mengukur jumlah garis-garis gaya yang melintas pada permukaan seluas 1 meter persegi. Nah, yang di 1 meter persegi itu kita sebut satuannya Weber. Jadi itu satuan dari medan magnet yang diukur pada intensitas kekuatan medan magnet. Jadi magnet density bahasa Inggrisnya. Nah, sekarang supaya mudah mengingat, kalau kita mempunyai magnet, sejumlah garis-garis gaya magnet keluar, garis-garis gaya itu disebut flux magnetik, sejumlahnya yang melewati sebuah permukaan itu kita sebut sebagai kerapatan magnetik, jumlah garis-garis gaya tersebut ditentukan oleh kemampuan electric field atau medan listrik mengeluarkan atau memindahkan elektronnya alias arusnya berapa. Karena itu kalau mau memperbesar arah pancar dari yang namanya antena, kita kuatkan powernya. Powernya dikuatkan, maka di antena tersebut kita konversi electric field itu menjadi magnetic field. Siapa yang mengkonversi? Model antenanya atau konduktor yang dilewati electric field tadi, mengkonversi, mengubah dari electric field menjadi magnetic field sehingga dia bisa meradiasi atau berpindah secara transversal di udara. Udara itu kita sebut mu nolnya nanti. Mu nolnya. Mu nol itu apa berarti nanti? Permeability atau permeabilitas. Nah, disitulah sebenarnya konsep ketika kita mau mengatakan bahwa HP kita itu ada sinyalnya. Kenapa? Karena sinyal tersebut dimiliki oleh medan elektromagnetik. Kenapa bukan namanya medan magnetik saja? Kenapa ada elektroknya? Karena yang membuat ada garis-garis gaya magnet itu ketika yang namanya ada arus dilewatkan pada konduktor ya, jangan sampai lupa. Konduktor yang sifatnya berfungsi sebagai memindahkan elektron mencari proton supaya terjadi kesetimbangan. Di situ konsepnya apa? Apakah konduktor 100%? Iya. Nanti kalau di pelajaran antena kamu akan mendapatkan konsep bagaimana sebuah antena itu bisa membuat gelombang itu berjalan seperti yang diinginkan. Nah, itulah nanti ketika Anda mempelajari ya yang namanya beamwidth atau lebar beam yang dikeluarkan oleh antena tergantung oleh model-model antenanya sendiri. Jadi tipe-tipe bodinya antena menyebabkan model beamwidth yang bermacam-macam, dan model beamwidth tersebut akan model beamwidth itu akan membuat yang namanya konsep gelombang elektromagnetik itu akan berjalan atau bertransversal di udara sejauh yang dia mampu. Yang dia mampu sejauh mana? Nah, ini pertanyaannya. Sejauh dari kemampuan dia menempuh jarak. Karena ada yang kita sebut sebagai pelemahan atau losses di jalan. Kok ada losses? Kenapa? Karena ada yang namanya medan magnet bumi juga diserap oleh bumi. Nah, ini yang kemudian diwujudkan informasinya dalam judulnya field strength atau kuat medan. Disitulah kita nanti mendapatkan yang disebut adalah coverage area. Nah, itu ringkasan dari mengapa kita mempelajari electric field dan magnetic field terpisah, tetapi hasilnya digunakan untuk menerjemahkan satu fenomena yang kita sebut sejauh mana kita bisa mendapatkan sinyal apabila kita ingin berhubungan secara wireless. Itu kalau kamu terjemahannya di lapangan seperti itu. Oke ya, 17.43 aku rasa sudah cukup kita mengawali untuk pemanasan menuju informasi selanjutnya. Jangan lupa tadi sudah dibilangkan pada yang ada ibunya dari India tadi bahwa B atau B itu apa? Kerapatan flux magnet atau kerapatan garis-garis gaya magnet ketika diukur menggunakan integral tertutup atau closed loop, di mana integral itu berjalan dari satu titik dan berakhir di titik yang sama, maka nilainya adalah 0. Kenapa? Karena saling meniadakan. Atau di situ kita ngomong kok meniadakan kenapa? Karena ada arah yang berbeda. Kan ada arah utara sama selatan, timur sama barat gitu ya. Jadi ini kalau kita menghitung flux magnetik pada satu permukaan tertutup. Kenapa kok permukaannya tertutup? Karena kita ngomong medan. Medan itu selalu permukaan yang tertutup. Tidak pernah medan itu yang namanya medan itu permukaannya terbuka, enggak. Mesti kita mempunyai semacam kayak luasan tertentu. Luasan tertentu tuh kalau kamu start, kemudian kamu mengelilingi, kamu kan berhenti di titik yang itu juga gitu ya. Jadi finish sama startnya itu sama titiknya. Karena itulah kita akan mempelajari berikutnya bagaimana cara kita melihat karakter ketika kita mempelajari kerapatan garis-garis gaya magnet. Kita gunakan persamaan Maxwell. Nah, semoga minggu depan yang join bisa lebih banyak ya, supaya bisa lebih memahami fenomena, karena pada akhirnya kita nggak perlu mengerjakan yang namanya rumus itu dengan input angka, tetapi kita perlu memahami rumus itu sebagai perwujudan dari proses bagaimana karakter sebuah medan elektrik itu bisa mempengaruhi timbulnya flux magnetik atau garis-garis gaya magnet gitu ya. Itu yang kemudian aku tag pada screenshot. Pada screenshot yang sudah aku kirimkan di grup. Oke ya. Terima kasih untuk Afif atas share screen-nya. Minimal saya punya teman untuk berada di etol. Semoga minggu depan bisa full tim ya untuk bisa masuk dan mempunyai engagement dengan kemampuanmu untuk menganalisa. Jangan lupa kamu tetap harus menjalankan prosedur pemahaman ya, walaupun mungkin matematikanya agak-agak bikin ngeper gitu ya, karena memang ini matematikanya levelnya sudah level advance. Tapi apapun yang nanti kita dapatkan di ujung-ujungnya, kita tidak lagi berurusan sama matematika, kita berurusan sama konsep bagaimana membaca fenomena itu berdasarkan sebetulnya rumus matematika yang bisa diwujudkan. Jadi konsep rumus matematika ini sebetulnya cara untuk menjelaskan konsep gaib yang terjadi pada saat kita melihat gelombang elektromagnetik yang nggak bisa kelihatan mata. Kalau umpamanya ditanya, Bu, kenapa yang namanya ada besi itu kan persamaan 7.32 ya, yang kayak garpu itu sama dengan integral B itu adalah flux density-nya atau magnetic flux density-nya, kerapatan flux magnetik dot ds. Kenapa enggak cross ya? Itu kemarin sudah kita bahas ya. Ini kita dot. Tadi ada juga di yang pertama. Kalau flux itu adalah vektor, kalau satunya adalah skalar gitu ya. Ada informasinya seperti itu. Itu bagus sekali itu. Nah, itu yang kemudian bisa menjelaskan kalau yang namanya seperti garpu itu bacanya besi, itu adalah satuannya Weber, makanya dia menggunakan dot, karena dot itu nanti mengacu pada skalar. Sedangkan cross itu pasti dia itu mengacu pada unit vektor yang sifatnya muter, kan ya kemarin ya ada AX, AY, AZ kalau yang namanya cross itu. Jadi itulah kenapa kalau ditanya, Bu, sebetulnya kita unit vektor dot dan cross itu sudah nggak kepakai lagi ya. Itu adalah tool selamanya akan dipakai kalau mau mempelajari electric field sama magnetic field. Nah, itu ya mungkin supaya lebih tenang gitu ya, coba dilihat-lihat lagi dan pasti insya Allah kalian bisa semua karena sudah kupilihkan how to memorize, bagaimana mengingat dengan mudah konsep-konsep yang kita punya. Ya semudah-mudahnya sih memang tidak ada yang terlalu mudah, tapi bukan sesuatu yang mustahil kalau kita mempelajari. Akhirul kalam 1749 ya, Boki mengucapkan minal aizin wal faizin taqabbalallahu minna wa minkum, untuk seluruh yang mendengar mungkin sudah berkurang ya ini ya. Semoga kita dimudahkan dalam mempelajari ilmu-ilmu Allah yang luar biasa banyaknya dan tetap tidak berputus asa ketika kita mengharapkan rahmat paham dari ilmu-ilmu yang sudah ada di alam. Aku end meeting, terima kasih untuk join-nya ya. Semoga next week lebih banyak. Selamat sore, Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh.